Let's apply that law of exponential growth and decay. I have written the law up here so that you can reference it. Now, just so you know, most of the time we apply this law, we do these problems in several different steps. To understand that, I'm actually going to do example number 3 before I do example number 2. In example number 3, you'll kind of see that usually these problems are done in more than one step. Usually the first step is to find k, and then the second step is applying what you learned for k. So let's look at this. Example 3. The first sentence says, let Y represent the mass in pounds of a radioactive element whose half-life is 4,000 years. Now that phrase right there is actually all we need to know in order to find k. First off, let's talk about what half-life is. Half-life means that it takes 4,000 years, let's see, I did that with green, 4,000 years to go from however much you started with to half that amount. So if I start with 1 pound, after 4,000 years, I would have half a pound. And it doesn't actually matter what number you have here. All that matters is that this is half of what is there. So I could do 6 here and 3 there. And you'd still be good and get the same k. That relationship of being half just needs to hold. Now I've got this. So I need to use this half-life of 4,000 years to solve for k. So I have ln of 1/2. This 1 is just going to go away because 1 times anything is itself. And then the ln and the e cancel. So ln of 1/2 equals 4,000 k. And divide by 4,000 to find out what k is. Now, this is a really big calculus trick. If I open up my calculator and I type this in, ln of 1/2 divided by 4,000. Enter. I have this gross big long decimal. If you approximate this decimal to whatever, you round it, I should say. If you round that decimal, I guarantee you will get this problem wrong. Because our final answer over here needs to be accurate to 3 decimal places. And if you round anywhere in the middle, this answer, this final answer, is not going to be accurate. So there is a trick that we use for our calculator to store this answer. So store. And you should see a button on your calculator that says STO and then a triangle. So we see it right there. If I click that button, I am telling my calculator to store this answer as a variable. So I get to pick. Now you may have noticed these green letters on your calculator. You hit alpha to get to those green letters. Now this is k, so I'm going to find k right there and do alpha parentheses, and I get that k. And enter. So this is essentially telling your calculator that anytime I type k, you're going to use this number instead. And your calculator is using the entire number, not the rounded number. So this is way more accurate. So anytime you get this big decimal, you're going to want to store it as a letter so that your calculator isn't using the rounded decimal, it's using the whole answer. It's way more accurate. So I have stored this as k in my calculator so that anytime I use alpha parentheses and type k, it's going to use that number instead. So I just say I'm storing that. And that's what you can do on your AP test too. You just make a note of, I stored this answer as K. Now let's go to step 2, where we apply K. So here's our second sentence. If there are 200 pounds of the element, so that is our C in an inactive mind, how much will remain? That is a Y question. How much is left in 1,000 years? There's my T. So I want to find Y. I'm given that C is 200. I know that my K is stored. And I know that my T is 1,000. So now what I can do is just type all of that into my calculator, and I'll get an accurate answer because K is stored. So I go into here, and I type 200 e to the 1,000 times, and I do my stored K, alpha parentheses, enter. And it says express your answer to 3 or more decimal place accuracy. So 168.179. And this is pounds. So after 1,000 years, if we start with 200 pounds, there will be about 168 pounds left. And we know that answer is accurate because we didn't round K, we stored it. And that's how most of these problems usually go. You use something to find K, but then your final answer is actually applying K. So now that we know that, let's go back up to example 2. This is a much simpler problem because this problem is just asking you to find K. You don't need to apply it. So let's read through this. What is the rate of growth, that's my K, in a city whose population triples? That triples is kind of like your half-life. That's going to tell you Y and C. So we know that it triples every 100 years. That's our T. So let's go into here, write what we know. We're trying to find K. I know that T is 100. And I know that my population triples every 100 years. So that means if I start with 1 person in my population, after 100 years, sorry, that should be pink. After 100 years, that population will triple to 3 people. Same thing with half-life. It doesn't matter what you put there as long as this is triple what that is. So I could start with 100 and 300. I could start with 2 and 6. Any of those. Now this problem is just a solve for K. We don't need to apply K in a second part. So what I'm going to do, I'm going to take the ln of both sides so I can get rid of that e. That 1 doesn't really matter. So I get ln of 3 equals the ln and the e cancel. 100k. Divide by 100. So I get k equals ln of 3 over 100. Now, I don't need to store k this time because I don't need to apply k. This is my final answer. So I'm going to type this in, ln of 3 divided by 100. That's what I get. And it says express your answer as a percent. So I need to take this answer and move it 2 over to get a percent. So I got 1.098%. And it says rounded to the nearest hundredth of a percent. So I'm going to round to the nearest hundredth, which is that. So I need to round up to 1.10%. And that should be my final answer. In the last video, we'll do one last example of exponential growth and decay using Newton's law of cooling.